Opamp with common input. What is meant by this? See, so far we have gone through some Opamp circuits where the input is applied to either inverting or non-inverting input terminals or to both. Okay, something like we applied a V1 here, V2 here, and we found the output, etc. Now, instead of giving two different inputs, we give a common input to both inverting and non-inverting terminals. That is known as op-amp with common input. So how do we find the output of this particular case? See this. So this is Vi, means V plus, voltage at the non-inverting terminal. Due to virtual short, voltage at the inverting terminal is also Vi. The basic procedure is just we take the node equation here and find the output. Alright, of course, this is a special case. What you can observe here is whatever the current that is flowing through R2, the same current will be flowing through R1 as well. We are well aware. Because no current enters into any of the input terminals like inverting or non-inverting terminals. Okay, then what about this current I? Here it is Vi, here it is Vi. So there is no potential difference and hence the current is 0, which means I is 0. Then here it is Vi, here it is V output, and there is no potential, right? There is no current flowing between this node and this node, and hence so it is possible if and only if both the voltages are same, means V output is equal to input. Just like that we can write, and the circuit behaves like a voltage follower. Okay, here output is independent of R1 and R2. Whatever may be the values of R1 R2, we need not bother. Okay, this is how simply we can write the output. We can find the output. Instead of that, the regular method means nodal analysis. Anyway, we have seen this answer, right? It is the easiest way to find R1, R2, Vi. See, this is Vi. Due to virtual short, it is Vi. Then let me take it as node A. Apply KCL at node A. What we can, Vi minus Vi by R2 plus Vi minus V output by R1 is equal to 0. Anyway, this term it is 0, Vi minus Vi implies V output is equal to Vi. As I said, the current that is flowing through R2 is 0. So obviously output will be equal to V input. This is how we can write the things. Alternatively, right? Anyway, we can conclude here why I am writing means there is a reason why I am writing these many methods, right? Okay, alternatively, I am using superposition. R1, R2, and this is Vi and it is also Vi. Suppose I draw a circuit like this, and if I ask you to rig it up on breadboard or springboard, what you will do? Definitely you will join these two, means you will take this circuit only. You will rig it up, right? You will rig up the things this way only. Okay, even though I draw the circuit on the board like this. So it's as simple as it. So it's like you are giving two inputs. It is like V1 and it is like V2. So what is the output equation? It is 1 plus R1 by R2 into V1 minus R1 by R2 into V2. But both V1 and V2 are equal. So R1 by R2 into Vi minus R1 by R2 into Vi. So finally, what is your answer? Same way, which is looking lengthy. This is the simplest way to get the answer. Okay, so nothing to worry about it. See this, right? Why I wrote this one, superposition and all, right? We'll see that later on. Anyway, look at this question. In the ideal op-amp circuit given in the adjoining figure, the value of RF is varied from 1 kilo ohm to 100 kilo ohm. RF is varying, so the gain G is equal to V output by VI will remain constant at 1 volt, remain constant minus 1. Some options are given. Okay. See, even though you have this 10K, it doesn't play any role because this current is 0. So that once you remove this 10K, this circuit is same as that of the previous circuit we studied. This one only. Okay, and what about the output? Output is equal to input, or the gain is equal to 1, which is constant, remains constant at 1. Gain is 1. Gain does not dependent on the feedback resistor RF. That's it. Next, see the second circuit. Okay, I'm giving a common input to this circuit. Okay, so how do we write it further? As I told, so we can redraw the circuit this way. It is VI, it is VI, R1, R2, R3 and R4. So it is now acting like V1, it is acting like V2, and we know what is the output equation then. It is 1 plus R1 by R2 into the effect of V1, right? It is into R3 by R3 plus R4 into V1 means Vi minus R1 by R2 into V2, that is Vi only. That's it. It is as simple as that. Here I need not worry about calculating what is V plus, again virtual short and take the node equation. That is a bit time taking procedure. Just if I redraw the circuit, right, this circuit is redrawn like this, so that just like that you can write the answer. Okay, that's what my concern. It's like right, you can use superposition or whatever it is. Once you have a circuit, the final result is this way. Then see this question. For the op-amp circuit shown in the figure, V output is, what is the output of this circuit? Same thing I'm using. V output is equal to, suppose 1 volt is appearing here, then what is the output equation? 1 plus 2 kilo ohm by 1 kilo ohm into 1 kilo ohm by 1K plus 1K into 1 volt minus 2K by 1 kilo ohm into 1 volt. Means what is the effector? If 1 volt is direct only applied here, it is minus 2K by 1K into 1 volt. So it is 3 by 2 minus 2. It is minus 1 by 2, means minus 0.5 volts is the answer. It's as simple as that. See, the circuit is appearing here like this. It looks like some bridge, but it is same as that of our previous circuit only. Okay, so directly I'm writing the answer. For the ideal op-amp circuit, a figure determine the output voltage. So what we can write, V output is equal to 1 plus 99 by 100 into 100 by 100 plus 100 into 4 minus 99 by 100 into 4. Okay, it is further written like 199 by 200 into 4 minus 99 by 100 into 4. Let us multiply and divide with 2. So I can take 4 by 200 common, so that it is 199 minus 99 into 2, it is 198. Just mathematical rearrangements only. There is nothing special about it. So 199 minus 198, it is 1 1, right? 4 by 200, 4 by 200 means 1 by 50, 0.02. That's it. Volts. Okay, that's it. It's as simple as that. Next, for the ideal op-amp circuit of the figure, determine the output voltage. Okay, the input is applied between these two terminals. It's not like applying here and here, between these two. Okay, then how do we do this problem? Okay, see this. See, suppose I'm taking some current I leaving the source. Whatever the current that leaves the source, the same current has to enter. No doubt about it. So, from where this I has to come, here no current is possible. So, entire current has to come like this only. Again, here also no current is possible. And hence, entire I will be going this way only. Is it not so? First, you observe the path of the current flow. Okay, next, this voltage is V plus and it is V minus. Let me take this voltage as some Vx, which is equal to V minus minus V plus. So Vx is equal to V minus minus V plus, whose value is 0, virtual short. Physically no connection, but virtually both are at the same potential and the Vx value is 0. Okay, then let me take this loop equation. Let me take this loop equation. What we can write? Minus Vi plus I into R2 plus Vx plus I into R2. I into R4, sorry. Anyway, Vx is 0. So, I into R2 plus R4 is equal to Vi. Keep it aside. Ri is equal to Vi by R2 plus R4. Okay. Then what about V plus or V minus? So V minus is equal to V plus is equal to minus I into R4. That is minus Vi into R4 by R2 plus R4. Keep it aside. What about V output? V output is voltage across R1 plus voltage at this point with respect to ground. So I can write V output is equal to minus I into R1 plus V minus. Is it not so? Voltage at this point with respect to ground. Ground means this level. So voltage across R1 plus voltage at this point with respect to ground. So it is further written like I is equal to, right, Vi by R2 plus R4. Of course, that is multiplied with R1 plus V minus means minus Vi into R4 by R2 plus, sorry, it is R3. So finally what we can write? Minus of R1 plus R3 by R2 plus R4 into Vi. So this is the output equation. Okay, so R1 plus R4 by R2 plus R4 with the negative sign. Okay, so in the same circuit, suppose, okay, here place is not permitting, I am just writing here. In the same circuit, if I take all equal resistors and I am changing the polarities of input, then what is the output, friends? So here V output is equal to, see here Vi polarities are from top to bottom, now bottom to top, means no negative sign comes, and all are equal means right? It is R plus R by R plus R into Vi. So output is equal to input. No negative sign. Behaves like a voltage follower. This circuit will also behave like a voltage follower. If I change the polarities of the input and if all the resistors are equal, okay, or R1 plus R3, if R1 plus R3 is equal to R2 plus R4, that is also fine. Then circuit behaves like a voltage follower. But generally we take equal resistors. Okay, this is one possibility. Okay, you cannot apply superposition here. You cannot break the source. The source is connected between R2 and R4 here. Okay, it's not like here R2 is at some potential with respect to ground, and R4 is also connected to some source with respect to ground. No, between R2 and R4 the source is connected. Source is a part of this whole loop. You can see, right? The next one, op-amp with both negative and positive feedback. See, so far we have seen the op-amp circuits with negative feedback. And with positive feedback, I told if you have only positive feedback, output of the op-amp is either plus or minus V set. I told that. Okay, now I'm having an op-amp circuit where the feedback is a combination of both negative and positive. So how do we do this problem? Right, this kind of things. See, directly I take one example. Right here, it has there is a feedback connection, output to inverting terminal as well as from output to non-inverting terminal we have the connection. Okay, so initially what we do is we apply a virtual short and we proceed. Okay, we do the calculations and later at the end we will see the output. From the output value we can check what kind of feedback is dominating. By default what we take is negative feedback is dominating. Whenever you see an op-amp circuit with both positive and negative feedback, what we do, assume that negative feedback is dominating and gain is anyway infinity, so that we can apply virtual short. So assume negative feedback is dominating. And apply virtual short. As nothing is mentioned about the gain, we assume AOL is tending towards open loop gain is infinity. Okay, then how to analyze this circuit further? See, from output, whatever the current comes, entire current will go like this only. No current enters into this non-inverting terminal. If so, what is the voltage at this point? V plus. What we can write for V plus? V plus is equal to V output by voltage division rule, 100K plus 10K into 10 kilo ohm. That is V output by 11. Then once you know V plus and this voltage, then what is the output equation? V output is equal to 1 plus 10 kilo ohm by 5K into voltage at the non-inverting terminal minus 10K by 5K into 2. Or you can take virtual short here, take the node equation, ultimately you get the same result, no doubt about it. So it is 5 2's and 3 into V plus, it is V output by 11 minus 4. Okay, further 3V output by 11 or V output minus 3V output by 11 is equal to minus 4. So it is 11 minus 3, 8. 8 V output by 11, it is equal to minus 4, 4 2. So V output is equal to minus 5.5 volt. That's it. Of course, in this problem, the supply voltages are not given. Suppose the supply voltages are given like 15 and minus 15, then our answer is correct. No doubt about it. Because it is less than or as minus 15 less than V output less than plus 15 volts. Okay, our assumption is correct. Whatever I assumed, my assumption is correct. No doubt about it. Okay, suppose during the calculations, if you get output is greater than plus or minus, right, exceeding the limits, then our assumption is wrong and we will settle to the possible value. Means, suppose our output is instead of minus 5.5 minus 15.5 volt, then what do you take? Or minus 16.5 volt, then what do you take? Not possible. It is less than V output minimum, not possible, then output is equal to minus 15. That's it. Like that we proceed. Initially, we assume that negative feedback is only dominating and we calculate the output. And if it is within the limits, then we go with our assumption. If not, then our assumption is wrong and we take output is equal to either minimum value or maximum value. We don't know. Unless you complete the calculations, we cannot get the things. Okay, this is how we do the calculations. Okay, whenever you have an op amp with negative and positive feedback, you please do remember and do the proceed. We will proceed with virtual short and all, we calculate the output. And once the output is out of the limits, then only our assumption is wrong. Otherwise, we can conclude the answer we have got. Next, see this. Okay, the output voltage of the circuit shown in figure is, what is the output? Again, here there is no current possible. So entire current will go like this only. So this is V plus. I can say this is V plus, means this is also V plus. What is V plus here? It is V output by 2K plus 3K into 3K, voltage division rule. 3V output by 5. Okay, so it is V minus. So due to virtual short, V plus is equal to V minus is equal to so. And what about V output? V output is equal to voltage across the feedback path plus voltage at this point with respect to ground. We can take. So what is the current that is flowing here? It is 1 milliampere. So V output is equal to minus 1 milliampere into 2 kilo ohm plus V minus. So it is minus 2 plus 3V output by 5. So V output minus 3V output by 5 is equal to minus 2. It is 2V output by 5 is equal to minus 2. So V output is equal to minus 5 volt. I am directly writing it. So option D is correct. Okay. Next. See here. It also, right, if you look at this, there is a negative feedback as well as positive feedback in this case. Okay. The output voltage of the circuit shown in figure. Okay. So V output is here, as there is a direct connection from inverting terminal to output. So due to virtual short, it is also V output only. V minus is equal to V plus is equal to V output. Okay. And let me take this voltage as some VA. And from VA, whatever the current comes, entire current goes like this only. No current is possible in this direction. Okay. Then let us take the node equation here. Let me take KCL at node A. 1 milliampere is entering. So 1 into 10 minus 3 is equal to, entering current is equal to leaving currents. That is VA by 3 kilo ohm plus VA, right? I can write VA by 6K plus 6K, I can write it. Okay. Otherwise, VA minus V output by 6K. Anything I can write it. And one more leaving current, that is VA minus V output by 6k. Okay, the same thing it is repeating. VA minus V output by 6 kilo ohm. Okay, 3 leaving currents and 1 entering current. So here VA by, right, anyway 1 milli, no, right, I can cancel milli, right, because 10 power minus 3, right, can be written like 1 by 10 cube, that is cancelled, and 1 is equal to VA by 6 plus VA by 6, that is VA by 3, VA by plus VA by 3, 2 VA by 3 minus, okay, V output by 3, and 3 get cancelled. Okay, see here, keep this as equation 1, sorry. So V output is equal to, just if I take this, what is the relation between V output and VA? V output is equal to VA by 6k plus 6k VA by 2, or VA is equal to 2 times, okay, I can write it, so let me take it as equation 2. From 1 and 2, 1 is equal to, instead of, right, it is 2 by 3 into, instead of VA, I can write 2 V output minus V output by 3. So implies V output is equal to 1 volt. I can write so. Okay. That's it. This is how we can do it. Next. So multi-stage op-amp circuits. So connecting, so far we have seen only single op-amp. Now I'm connecting 2 op-amps, 3 op-amps in cascade or in series or parallel, and would like to find the output. Means the very basic thing we can see like this, minus plus. R1, R2, let me take it is Vi. Okay, output of this circuit is minus R1 by R2 into Vi, we are well aware. And let me take another op-amp circuit. R3, R4. Output of this one, let me take it as VO1. VO1 is acting as input to the second amplifier. So that what is the overall output? Okay, if you take it, so what is VO1? VO1 is equal to minus R1 by R2 into Vi. And what about overall output? It is minus R3 by R4 into VO1. That is minus R3 by R4 into minus R1 by R2 into Vi. Okay, so what is the overall gain? V output by Vi is equal to R1 R3 by R2 R4. That's it. Here we need not worry about the loading effect. See, what is the gain of the first stage? If you look at it, so multi-stage amplifiers like this, let me take it is A1, that is minus R1 by R2. And what about the gain of the second stage? Minus R3 by R4. So is it not equal to A1 multiplied with A2? Overall gain is equal to product of the individual gains, no loading effect. That's the advantage with op-amp. Okay, if we take with BJT, we observe that there is a scope of loading effect, but here we need not bother. Okay, that is the idea, and it need not be, right, inverting, both inverting. One is inverting, other is non-inverting. Possible, doesn't matter. Okay, so see this. Whatever the combination you like, you can take that. Instead of giving input to inverting terminal, I am giving to non-inverting terminal like this. Okay, R3, R4, R1, R2 and VI. What is the gain of this circuit? I can write A1 is equal to minus R1 by R2. What is the gain of this circuit? 1 plus R3 by R4. So what is the overall gain? Product of the individual gains. So overall gain A is equal to V output by VI is equal to A1 into A2. Or I can write VO1 by VO2. Sorry, VO1 by VI into V output by VO. So the final answer is minus R1 by R2 multiplied with 1 plus R3 by R4. That's it. So very simple, right? You can take a non-inverting first and inverting later. It doesn't matter. Ultimately, overall gain is equal to, as they are in series, right? Overall gain is equal to product of the individual gains. That's it. Okay, directly we can write this. I'm not writing more combinations, not required, right? Now, see this question. In the circuit shown below, the op-amps are ideal. Then V output in volts is. What is the output of this particular case? Okay, so even though you have this 1K, we need not worry about it. And let me take this voltage as VO1. What is VO1? Two inputs are given. So the output due to this 1 volt is 1 plus 1K by, 1 more 1K multiplied with 1 volt minus 1K by 1K into minus 2. We can take it so. So it is a 2 plus 2, it is 4 volts. VO1. And what about the overall output? It is now looking like a basic non-inverting amplifier. So output is equal to 1 plus 1K by 1K into VO1. It is 2 into 4, 8 volts. So option C is correct. It's a very, very simple question. Right. Find the output voltage V output in the following circuit. Assume that the op amps are ideal. How do we do this? Okay, see, if this 1K is not present, then this is VO1 and output is equal to, right, we can write overall gain is equal to product of the individual gains and all. But this 1K, that will definitely influence the circuit like anything. Then if you see something different, what you do is go with a basic procedure. Apply virtual short, take the node equation, you will get the final answer. No doubt about it. Okay, see, these are all the summaries of the node equations only. This is the summary of the final, right, node equation. If I apply virtual short here and take the node equation, then what is the result? You know. And here applying virtual short, and if I take the node equation here, what is the output? You know the result. That directly we know it's standard circuits we wrote. But it is not looking like the regular standard circuit. So let us apply virtual short and proceed. Due to virtual short, it is V plus is equal to V minus is equal to 1 volt. Let me take this voltage as VO1. Okay, and due to virtual short, it is 2 volts, means this is also 2 volts. Then by taking KCL at node A, we can find VO1. Once you get VO1, by applying KCL at node C, we can find what is V output. That's it. Don't apply any node equation at B, no meaning. Anyway, so node A, KCL at node A. One minus 0 by 2K plus 1 minus VO1 by 2K plus 1 minus 2 by 1K is equal to 0. So anyway, kilo is cancelled everywhere. So 1 by 2 plus 1 by 2, that is 1 minus VO1 and minus 1. So what I can write, 1 or 1 by 2 plus 1 by 2 minus VO1 by 2 minus 1 is equal to 0. So from this, what is VO1, friends? It is simply 0. Is it not so? Okay. By taking this node equation, we got the voltage here. Next, this voltage is known and this voltage is known. It is like simple adder circuit. Okay. Right. Right. Anyway, here also we have one more input. Nothing to worry. So what we can do? KCL at node C. So it is 2 minus 1 by 1k plus 2 minus VO1. VO1 is 0. So 2 minus 0 by 2k plus 2 minus V output by 2k is equal to 0. I hope you get the point. Okay. VO1 value is found to be 0. That's why directly I substituted that. Then anyway 1k, right, kilo got cancelled. Further 2 minus 1, it is 1, 2 by 2, it is 1, 1 plus 1 plus 2 by 2, it is 1 minus V output by 2 is equal to 0. Implies V output is equal to 6 volts. Okay, this is the answer. This is how we do the problem. And if you think like, right, directly I will take this voltage as minus 2k or 1 plus 2k by 2k into 1, that is, you will get 2 volts, which is absolutely wrong. That's what you get in the absence of this 1 kilo ohm. Because of this 1k, entire circuit got changed. We have to go with the basic procedure. Apply virtual chart, take the node equation, that's it. Okay, right. If you do not have that consciousness, just like that, you lose the marks. And it is much easier even compared to networks. See, network analysis, you do lot of logical tricky things. But the advantage with analog, once it's like an application of networks. Just you are applying KCL, and while applying that KCL, you should be very careful. That's it. See this question. Find the output voltage of the following circuit assuming ideal op-amp behavior. Okay. See, first of all, let us take this voltage as VO1. Once you get this VO1, then we can do the further calculations. How to get it? I should know this voltage. How to get this voltage V plus? See, from V output, whatever the current comes, entire current will go down like this only. So V plus is equal to V output by 7 kilo ohm plus 1 kilo ohm into 1k, that is V output by 8. Keep it aside. Once you know the voltage here and the voltage here, how to write V output 1? VO1 is equal to 1 plus 2 kilo ohm by 1k into V plus minus 2k by 1 kilo ohm into 1 volt. It is 3V output by 8 minus 2. Keep it aside. Next, I know the voltage here and the voltage here. Then how to write V output? V output is equal to 1 plus 8k by 2k into 1 volt minus 8k by 4k into VO1. So 8k by 4k, 4 2's, it is 3 minus 2 into 3V output by 8 minus 2. Okay. How much do we get from this? It is 7 minus 3V output by 4. Okay. Then V output plus 3V output by 4 is equal to 7. So V output is equal to, directly I am writing, it is 4 volts. Okay, that's it. This is how we can do this problem. It's a very simple thing. There is nothing, no logic in it. Look at this question. It's a similar one. Okay, here 1 volt and minus 1. I think data is also same. 1k, 2k, 4k, 8k, yes. And 3k and 1k are given here. Instead of 7k, 1k, right, it is, instead of 7k, it is a 3k is given. And here 1 volt, here 1 and minus 1. That's it. Only this resistor and this value are changing. I hope the students can do this problem. I do not want to waste the time in doing such repeated one. Anyway, as it's given in the previous paper, I wrote it. Right? You can just try this question. Look at this. The V output by V input of the circuit shown in figure. It's a recent papers only, maybe 2023 or GATE 2022. Right? We can understand that it is something like an adder, inverting adder, right? So let me take this as VO1 and this one as VO2. So what is V output? Minus R4 by R3 into VO1 minus R4 by R3 into VO2. That is for sure. And what about VO1? The same input is given to this op-amp and this op-amp. So VO1 is equal to minus R2 by R1 into VI, right? Or let me write V output, it is equal to minus R4 by R3 into VO1 plus VO2. And VO1 and VO2 minus R4 by R3 into VO1, it is minus R2 by R1 into VI. And what about VO2? It is non-inverting amplifier. It is 1 plus R2 by R1 into VI. Is it not so? So, and if you observe this, minus R2 by R1 into VI plus R2 by R1 into VI get cancelled. So, it is minus R4 by R3 into VI. So, what is the gain? It is V output by VI is equal to minus R4 by R3. Option A is correct. It's a very simple question. It's a two. It was asked for 2 marks. Nothing is there in this. So, it is simply inverting adder. Summing amplifier, I can say. Adder or summing amplifier. Okay. All the resistors equal means I can say adder. It's a summing amplifier. Right. Next. For the op-amp circuit shown in figure, determine the output voltage, assuming that the ideal op-amps are ideal. Okay. See, the circuits appear so, but there is nothing in that. Generally, what we do, apply virtual short and take the node equation I told. Due to virtual short, it is 0 volts. Let me take this as node A. Okay. Then, before taking this node equation, you see, we think of this voltage because here also there is a node. But is there any current that is possible here? No. Means whatever the current comes here, the entire current will go up here only. Which means 2R and 3R are in series. As there is no current possible into the inverting terminal of this amplifier A2. Okay. So what we can write here, let me take this node equation KCL at node A. It is 0 minus Vi by R plus 0 minus V output by 2R plus 3R is equal to 0. So V output by 5R is equal to minus Vi by R. R output, no, they are asking V output is equal to minus 5 into Vi. That's it. Gain is minus 5. Okay. Determine V output in the op-amp circuit shown in figure. Anyway, assuming ideal op-amp. How do we do this? The regular procedure. Don't afraid of the circuit. Just you stick to the basics. Apply virtual short. This is V2 and let me take it as node A. And output of this op-amp, let me take it as VO1. Apply KCL at node A. Okay. And anyway, due to virtual short, it is V1. Sorry, not V2, it is V1. Okay, KCL at node A. What you can write? V2 minus 0 by R2 plus V2 minus V1 by R1. I am writing it as the circuit is looking something new, but you know it is something like a non-inverting amplifier. So right, if it is connected here, then what you might have written, the output or the voltage. What is the summary of the node equation here? 1 plus R1 by R2 into V2. That's what you are going to get here also, nothing else. Okay, V1 is equal to 1 plus R1 by R2 into V2 you will be getting. Anyway, so here V2 into 1 by R2 plus 1 by R1 is equal to VO1 by R1. Let us take this R1 to the left hand side, so that, which implies VO1 is equal to 1 plus R1 by R2 into V2. Keep it aside. So by taking this node equation, we got the voltage at this point. Next, right, after virtual short, you are taking voltage here, node equation here. Similarly, after virtual short, take the node equation here. Let me take it as node B. Don't take node equation here, because we do not know this current. Some current will be going like this, which is unknown. We do not know what is this current. So don't apply any node equation here. Be careful. Then take this node equation. Anyway, we know this voltage. Okay. So this voltage is known, this voltage is known, and this voltage is known. What is the point in taking this node equation? If you want to find this current, then you can think of taking that node equation. Right, I is leaving I plus VO1 minus V2 by R1 plus VO1 minus V1 by R1. You can write so that you can find what is I. But my concern is not to find I. My concern is to find V output. What we can do. Anyway, right, I'm taking this node equation. KCL at node P. Then it is V1 minus VO1 by R1 plus V1 minus V output by R2 is equal to 0. Okay. So it is V1 into 1 by R1 plus 1 by R2 minus VO1 by R1 is equal to V output by R2. What is V1? Okay, anyway, V1 is known. And what is VO1? Sorry, it is VO1 by R1. So V1 into 1 by R1 plus 1 by R2 minus, or let me take this R2 to the left hand side. Okay, I'm just minimizing the steps, nothing else. Minus R2 by R1 into, what is VO1? It is 1 plus R1 by R2 into V2 is equal to V output. Now further what we can write, V output is equal to R2 by R1 plus 1 into V1 minus, right, if I take this R2 by R1 inside, R2 by R1, okay, plus 1 into V2. Or I can write it is equal to 1 plus R2 by R1 into V1 minus V2. Means output is equal to some gain into V1 minus V2. Is it not acting like a differential amplifier? Means above circuit behaves like a differential amplifier. That's it. Okay, it's a very simple one. We studied already a differential amplifier. There we used only one single op-amp. Here I am using two op-amps. And what is the overall gain? It is 1 plus R2 by R1. The differential gain, I can say. Okay. We'll see its application also later. And okay, look at this one. It's similar to the previous one, a bit slight extension. Nothing else. Okay. See, what is the voltage at this point? Here it is, let me take it is V plus. So V plus is equal to 5 by voltage division rule. Entire current will go like this: 20k plus 10k into 10k. It is equal to 5 by 3 volts. The same thing will be appearing here. Or once you know the voltage at the non-inverting terminal and the voltage here is 1, so we can directly write this voltage VO1. The summary of, or you apply virtual short here and take the node equation, you can find VO1. Or the summary of that virtual short and node equation, I can write here like this: VO1 is equal to 1 plus 10k by 20k into V plus this voltage, right? Anyway, V minus is equal to V plus, and minus 10k by 20k into this voltage, that is 1 volt. Okay, so it is 3 by 2 into 5 by 3 minus 1 by 2. 5 by 2 minus 1 by 2, it is finally equal to 2 volts. So by taking this node equation, we can get the voltage at this point. You can write the node equation if you want, nothing to worry. Okay, VO1. Next, due to virtual short, it is 0 volts. Then by taking this as node B, right, I can find the voltage here. Okay, if you want to find the current through this, then only you use this node equation. Otherwise, don't touch this node. Okay, so KCL at node B. Then it is 0 minus VO1. How much it is? 0 minus 2 by 40k plus 0 minus V output by 100k is equal to 0. So V output by 10 is equal to minus 1 by 2. I can directly write the answer anyway. So V output is equal to minus 5 volt. That's it. Okay. This is how we can do this. Next topic is voltage to current converter circuits. Okay. So a voltage to current converter is also known as a V2I. So first letter here, and instead of I, we write I. V2I converter is an electronic circuit that takes voltage as input and produces the current at the as output. Okay. And here, what is the importance why you are converting voltage to current? And means here the concern is the produced current will be independent of the load you are connecting. You are collecting the current across some load. Okay, and that does not depend upon the load impedance. That is the speciality here. And one more thing is, there are right some situations where the current producing devices are less noisy compared to voltage producing devices. And where do we use such kind of things? Means especially in transducers, right? You say if you observe in instrumentation applications and all, what we do, right? We can even transmit, or we can convert some non-electrical quantity to electrical quantity. The produced electrical quantity may be voltage or current. But if the produced electrical quantity is current, that is less noise and that can be easily transmitted compared to voltage. That's the main concern. Right, in such situations, mainly we use this right, voltage to current converter. Okay, so a voltage to current converter is an electronic circuit that takes voltage as input and produces current as output. In instrumentation circuits, sorry, when creating an analog representation of certain physical quantities like weight, pressure, motion, etc., DC current is preferred because DC current signals will be constant throughout the circuit in series from the source to the load. And the current sensing instruments have right, also have the advantage of less noise. They are less noisy compared to voltage sensing instruments. That's why we right prefer this voltage. In such situations, we use this voltage to current converters. And again, there are two types of voltage to current converters. So transducer output may be a voltage. So non-electrical quantity to electrical quantity. Right, you may get the electrical quantity as voltage or current. Suppose you get voltage, there you can use another voltage to current converter, so that that current is much comfortably transmitted compared to the voltage signal. That's the idea here. Okay. So there are two types of voltage to current converters. That is floating load voltage to current converter, and the second one is grounded load voltage to current converter. What is meant by this floating load? We'll see. Just the very basic circuit I'm taking here is like this. So floating load voltage to current converter. See, it's a basic non-inverting amplifier, nothing else. And the load resistor is connected here. The load is not physically connected to ground. It is a part of the circuit. The device you want to drive is connected here. RL in the sense it's a device. You want to drive some device. The device is connected here. Okay. So, how do we find the current through this? You see, let me take, right. Anyway, if I assume some current I, then the entire I has to go like this only. Means IL is equal to minus I. No doubt about it. And what is that value? IL is equal to minus I, where I is Vi minus 0 by R. Is it dependent on the value of load resistor? No. The device you are connecting in place of RL will experience a current proportional to input voltage. So, okay, negative sign will be there, right? Nothing to worry about it. So if the input changes, anyway R, this R is constant, so IL will change, and IL is independent of RL. Okay, that's why the name floating load. The load is not directly connected to the ground. And of course, right, once you are designing a system means the output should not be influenced by the load resistor, which is possible here. Okay, the basic floating load voltage to current converter, this circuit. Next, you need not worry about giving input to inverting. We can give input to non-inverting terminal also. See this again, due to virtual short, it is Vi, and if I take this IL, right, IL is equal to, right, earlier I wrote I, and directly I can take IL. Whatever IL comes, entire IL will be flowing to ground like this only. What about this IL? It is Vi by R. Simple. IL is equal to Vi by R. Voltage at this point with respect to ground, Vi divided by R. And that is independent of RL. Whatever may be the value of RL. RL may increase or decrease, doesn't matter. The device you want to drive is connected here. That's it. Don't worry about the output voltage. Here I am not interested in. I mentioned it. Nothing to worry about the output here. My load is here and the current through the load is fixed. It is decided by the input voltage. Here the input is given to non-inverting terminal, no negative sign. Earlier case, the input is given to inverting terminal, the negative sign has come. That's it. Okay. And one more thing we can see here. Right, instead of giving input directly here, right, just sometimes to confuse us, they may give the circuit like this. RL okay, then this is IL. What is IL? And V plus, we can write it. So IL is equal to, instead of Vi, what you have here? V plus by R. But what is V plus? It is Vi into R2 by R1 plus R2 multiplied with 1 by R. Like this also we can write. So nothing special about it. Anyway, once V input changes, automatically current through the load resistor will change. This is also a floating load only. The load is no way connected to the ground. Okay. either physically or virtually. It is not right connected to the ground. So look at this question asked in GATE 2007. A voltage source, right? The circuit shown in figure is, you see, right here, this is the load. It is like a voltage to current converter only, and this is some R. It is connected. It is V minus, sorry, V plus, and it is V minus. Okay. So what is V plus? It is equal to V by R1 plus R2 into R2. And due to virtual short, V minus is equal to V plus. And what about this is mentioned as load means this is IL, the same IL will be flowing here. So IL is equal to V minus by R, where V minus is equal to V plus is equal to, okay, V by R1 plus R2 multiplied with R2 multiplied with 1 by R. So here the circuit shown is a current source with current value, a current source with current value, this one, R2 by R1 plus R2 into V by R. That's it. Option D is correct. Next, look at this one. This is also right floating load only. Okay, in the Opamp circuit given in figure, the load current IL is, what is IL? So for better understanding of this circuit, what I am doing is, let me take this voltage as V1 and this voltage as V2. So V input is equal to V1 minus V2. I can write. Okay. So due to virtual short, it is V1, and due to virtual short, it is V2. Is it not so? So what is IL? IL is equal to this voltage and this voltage, the difference by R, V1 minus V2 by R. IL is equal to V1 minus V2 by R, where V1 minus V2 is nothing but our input by R. Okay, is it dependent on RL? No. Whatever IL comes, entire IL will go like this only. You see this, friends? It is coming from the output of Opamp 1, and it is going into the output terminal of Opamp 2. In between, there is no current division. IL will be flowing through RL and R. Okay, that's it. Here I am not looking at any voltage and all, just a load is connected. Current through that load is varying dependent on the input you are giving. So these are some circuits with a floating load, voltage to current converters. Okay, and grounded load, voltage to current converter. So here the input is given to inverting terminal. How do we analyze this circuit? Okay, so let me take this voltage as V output, and nothing to worry about V output. I am concerned about the current through the load resistor. That's it. And this voltage is V plus. Due to virtual short, it is also V plus, or V minus is equal to V plus. Okay. So let me take this as node A. KCL at node A. It is V plus minus Vs by R1 plus V plus minus V output by R1 is equal to 0. You see, these two resistors are equal. Okay. So R1 cancel. So V output is equal to 2V plus minus Vs, or V plus or V minus, are same. We can keep it aside. Okay. Next, let me take this as node B. KCL at node B. It is V plus minus 0 by R2 plus V plus minus V output by R2 plus IL is equal to 0. For IL, don't write V plus by RL, not required. Simply we can write IL. Because anyway IL will be independent of RL. Grounded load means the load is perfectly connected to the ground. Okay, the device you want to drive is placed here, nothing else. Okay, so then V plus by R2, V plus by R2, that is 2V plus by R2 minus V output by R2 plus IL is equal to 0. What is 2V plus? It is V output minus Vs. Is it not so? Okay. 2V plus is equal to V output minus Vs. So, or V output plus Vs, sorry, by R2 minus V output by R2 is equal to minus IL. So, V output by R2 minus V output by R2 will be cancelled. Or I can write here how I to change it. So, what is IL then? It is equal to minus Vs by R2. That's it. Okay. Not required anyway, you can understand that. Like this, we can write. Okay. Or instead of V output, you can write. Anyway, however you write, you will get the answer. It's not a big deal. Okay, instead of V output, what we can write? 2V plus minus Vs. Okay, so that 2V plus by R2, 2V plus by R2 cancel and minus Vs by R2 will remain. Okay, so not an issue. It's all about mathematical rearrangements. In the Opamp circuit given in the figure, the load current IL is, as right, it's the same previous one only. It is minus Vs by R2. See, these two resistors are equal and IL is equal to Vs by R2 with negative sign. And input is given to non-inverting terminal. How do we do it? Procedure remains the same. Let me take this as V output and it is V plus V minus is equal to V plus node A, node B. So, KCL at node A. And here you see R1, R1, these two should be equal and these two should be equal. All are equal, doesn't matter. But must and should condition is these two. The resistors connected to the inverting input terminal should be equal and the resistors connected to the non-inverting terminal also should be equal. RL is variable. We need not worry about RL. Okay. Then if I take it so, V plus minus 0 by R1 plus V plus minus V output by R1 is equal to 0. So V output is equal to 2V plus. Okay. Keep it aside. Next, KCL at node B. It is V plus minus Vs by R2 plus V plus minus V output by R2 plus IL is equal to 0. V plus by R2, V plus by R2, 2V plus by R2 minus Vs by R2 minus V output by R2. So 2Vs, 2V plus can be written like V output. So V output by R2 minus Vs by R2 minus V output by R2 plus IL is equal to 0. These two get cancelled. So IL is equal to Vs by R2. That's it. It is as simple as that. So you are giving input to the non-inverting terminal and hence no negative sign. You can even remember like this. It is IL is equal to right minus Vs by R2 in case of input given to inverting terminal and it is Vs by R2 in case of input given to non-inverting terminal. Alright, 2016 instrumentation paper. In the circuit given below, the op-amp is ideal. The value of current IL in microamperes is, okay, what is IL? It is Vs by R2. IL is equal to Vs by R2. It is like Vs and it is like R2. Is it not so? 1 by R2 is 10 kilo ohm. So 100 microamperes because they are asking in microamperes. That's it. And see this circuit. It was also asked in the previous GATE papers, maybe recently 2019 or 18. In the Opamp circuit given in figure, the load current IL is. The circuit is looking like clumsy. Don't afraid of it. Nothing is there in this. Just you need to have some confidence in doing such problems. Don't afraid of it. Okay, IL means this is also IL only. Is it not so? Okay, and let me take this is amplifier 1 and this is amplifier 2 whose output is VO1 and its output is VO2. So it is like a voltage follower. So this is VO2 and hence this is VO2. Is it not so? So IL is equal to VO1 minus VO2 by R1. I can write. Okay, that is independent of RL. RL may vary. We need not bother. Just this is what we can observe here. IL is equal to VO1 minus VO2 by R1. Okay. We need to find VO1 and VO2, then automatically we can do this. And we have gone through this kind of circuit earlier, right? When the input is applied between these two terminals, right? How to do the analysis and all we studied. Okay. See, let me take the current, some current I is living here, right? Whatever the, right, because it's a positive terminal, so current leaves the positive terminal and it enters. Whatever the current that is leaving the source, the same current has to enter. And how the current I will be going, it comes down like this and it goes this way. Okay. Next. Anyway, here no current is possible through this part into the inverting terminal. Let it be. Next, I is coming towards this terminal, means from where it has to come. It has to come like this only. It is I. Is it not so? Means, right, anyway, here I can take up to here only. But I don't know the current that is coming from the output terminal of A1. But current entering into the output terminal of A2 is no doubt I. Okay, here you can see this is some current maybe coming down or up, we do not know, and there is some current IL. So this I is not equal to IL. Please do observe this because there is a possibility of this current. Once you observe it, that is fine. Next, how to find I value? See, let me take it is Vx. Similar earlier also I wrote it. It is V minus, it is V plus. So V minus is equal to V plus and hence Vx is equal to 0. No doubt about it. Okay. So let me take this node equation, sorry, loop equation, loop 1. What I am writing is KVL2 loop 1 I into R minus V input plus I into R minus Vx is equal to 0. Okay. So, and Vx is of course 0. So, what I can write is V input is equal to 2I into R. Keep it aside. Okay. Done. Next. You see, here V plus minus VO2 is equal to I into R. This voltage is V plus minus VO2 is equal to I into R. Okay. Then VO1 minus V minus is equal to I into R. But to be frank, V minus is equal to V plus. No doubt about it. Okay. So, or I can write further what we can do is let me take this one as equation, this one as equation 1, this is 2 and VO1 minus, instead of V minus I am writing V plus is equal to I into R. So, if I add 2 and 3, 2 plus 3 implies, so V plus minus V plus, it is, they will be cancelled, it is, I am adding, no, so VO1 minus VO2 is equal to 2I into R. Means What is 2I into R? It is nothing but V input. VO1 minus VO2, that is equal to our input only. See the interesting point here. Okay. Are you observing? And I told you one circuit, this one minus plus. If I right take some circuit like this, R, 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 and VI from bottom to top polarities, it is acting like a voltage follower. Remember? Okay. So this circuit is something similar to that only. But here it is not connected to ground, but here it is connected to this particular point. Anyway, so which implies IL is equal to VO1 minus VO2, means it is V input by R1. And the same IL is flowing through RL. And it is independent of RL. The current through RL or the device you want to drive is connected in place of RL, that will experience a current proportional to the input voltage. Okay, that's it. This is how we can analyze this circuit. Okay. The next one is current to voltage converter circuit. Right. This circuit is appearing like this. So input should be current and output is voltage. This is where we are taking the output here. So first I am giving input to the inverting terminal, doesn't matter. And whatever IS comes, entire IS will be going like this only. And what about V output? Is as it is like an inverting amplifier, voltage across the feedback path looking from this direction is our output. Or due to virtual short, it is 0 volts. So 0 minus V output by R1 is equal to, right, IS. Implies V output is equal to minus IS into R1. Our voltage across R1 looking from output to input. That is our output. Is it dependent on RL? RL may vary. So the output voltage is proportional to IS. If IS varies, output voltage will vary. And of course, the output voltage is independent of RL. Hence the name current to voltage converter. Okay. So very basic level circuit. Okay, this is the question asked in previous papers. The circuit shown in figure uses an ideal op-amp working with plus 5 volts and minus 5 volts power supplies. The output voltage is equal to, what is the output here? Anyway, it is voltage across it. So this current is 1 milliampere. So it is minus 1 volt. Option D is correct. The circuit shown in figure uses an ideal op-amp working with plus 5 volts and minus 5 volts. Okay, power supplies, the output voltage is equal to yes. So here there is some resistor. Let it be. What is our output voltage? Voltage across the feedback path looking from output to input. Due to virtual short, it is 0. That's why I am saying. Okay, virtually 3K is connected to the ground. Voltage across 3K. What is the current flowing through 3K? It is simply 1 milliampere. Whatever the current comes here, entire current will be going like this only. So what is your V output? V output is equal to minus 1 milliampere into 3 kilo ohm. It is equal to minus 3 volts. Is it dependent on this 2K? No. Whether you connect 2K or 10K or 100K doesn't matter. That is not influencing the output voltage. So option D is correct. Okay. That's it. Next. Okay, the same circuit, right here some 5 volts is given. Nothing to worry. What is there? Now I can't take voltage across the feedback path as my output. No doubt about it. Okay. That is voltage across the feedback path plus voltage at this point with respect to ground. That's what we can take. Otherwise, due to virtual short, it is 5. And whatever 1 milliampere comes, entire 1 milliampere will be going like this. So I can write here 1 milliampere, that current is equal to 5 minus V output by 3 kilo ohm. So implies V output is equal to 5 minus 3, it is 2 volts. That's it. Or I can write V output is voltage across the feedback path plus 5. Voltage across the feedback path is minus 3 plus 5. The same answer you can see. Option A is correct. Current amplifier. Extension of a current to voltage converter. Okay, here the load, it is again a floating load. The load is not connected to the ground. It is a part of the circuit. So how do we find it? Whatever IS comes, entire IS will be flowing like this. We are well aware. And let me take this voltage as some V output. Anything you can write. Not an issue. Then this current is, and what about V output then? It is equal to minus IS into R1. Okay. And let me take this current as I2. So I2 is equal to V output by R2, that is minus IS into R1 by R2. Then you take the node equation. I0 plus IS is equal to I2, or I0 is equal to minus IS plus I2 is equal to minus R1 by R2 into IS. It is minus of 1 plus R1 by R2 into IS. That's it. Minus of 1 plus R1 by R2 into IS. It is independent of RL. Is it dependent on RL? No. Whatever may be the value of RL, doesn't matter. Now, output current is greater than input current. Negative sign is coming because we are applying input to the inverting terminal. Nothing to worry. That's why the name current amplifier. Same circuit, but data is given. Assuming that the operational amplifier in figure is ideal, the current I through 1 kilo ohm resistor is, what is I here? I is equal to minus of 1 plus this 2k by 2k into 2 milliampere. It is equal to minus 4 milliampere. That's it. It was asked for 2 marks. One, right? Anyway, you need not worry, right? Just like that, you can do the calculations. It's not a complicated circuit, right? So that's about these things, current amplifier. And next topic is finding the input impedance of a given op-amp circuit. We will see that in the next section. Thank you.